Howdy Rock Buds, Rock Papa here. Hope you guys are doing well today. Today we're going to talk about metamorphism and how it affects mafic rocks. And as you know, mafic rocks are rocks that have a lot of iron and magnesium in them and very little quartz in them. They're heavy and they're dark. We're going to look at the main kinds of mafic rocks that we find out there, and talk about how Greenschist metamorphism affects them and how Amphibolite Facies metamorphism affects them. We're going to look at pictures of all these rocks and all the metamorphic products that are produced via Greenschist and Amphibolite Facies metamorphism. So hopefully this video will be useful to you. If so, please subscribe. And thank you so much to all my most wonderful subscribers. I think about you all the time and appreciate you every day. So here we go. Metamorphism and mafic rocks. Okay, today we're going to be looking at the three most common mafic rocks that I know of: Basalt, Diabase, and Gabbro. And as we talked about before, mafic rocks are dark, rich in magnesium and iron. Mafic rocks are composed mostly of calcium-rich feldspar, and that would be labradorite most likely, and pyroxene. There might also be a little olivine. Okay, first we're going to talk about the mafic rock basalt. Basalt is mafic lava that's produced mainly in rifting situations and subduction situations. By rifting situations, I'm talking about a mid-ocean rifting ridge, or when a supercontinent like Rodinia rifts apart, and in subduction events where ocean crust is subducted beneath other ocean crust or beneath a continent, and you get stratovolcanoes with fractional melting where mafic, intermediate, and felsic magmas and lavas are produced. You get basalt lava in this situation, and usually this happens initially underwater, under the ocean. So here we got some pictures of basalt lava. This is basalt lava flowing from a Hawaii volcano. This is pillow basalt. It happens when basalt lava erupts underwater and it forms these funky little round pillows. Here's some basalt from Idaho, and you can see the white plagioclase or calcium-rich feldspar crystals easily. Here is some vesicular basalt also from Idaho, and you can see the holes where the gas bubbles came out there. This is basalt lava that has formed columnar jointing, where it forms these columns. It looks man-made, but it's natural. And here is a picture of one of the parts of perhaps the world's largest massive flood basalt flow. This is the Siberian Traps. Traps means steps because these mountains form steps. The Siberian Traps flood basalt occurred right around 250 million years ago. Supercontinent Pangaea first began to rift apart. This lava flow was so massive and went on for so long that it caused the world's most devastating extinction event called the Permian-Triassic extinction event. And here's a super cool picture of basalt at a mid-ocean ridge. Okay, we're talking Greenschist Facies metamorphism. You guys will remember that with Greenschist Facies metamorphism, temperature and pressure levels are relatively low, and water is usually very abundant. Basalt lava is an ideal candidate for Greenschist Facies metamorphism because it is surface flow. It flows out on the surface instead of flowing at great depth. And this usually results in metamorphic temperatures and pressures being fairly low. In rifting situations, the rift eventually results in an ocean where lots of ocean water is involved with the basalt. And in subduction zones, tremendous amounts of ocean water are subducted down into the subduction trench. And all this water facilitates later metamorphism at greenschist facies levels. Greenschist metamorphism is all about the transformation of existing minerals via hydration, where water is chemically added, and you get green colored hydrated minerals like chlorite and epidote. They give a green tinge to the rock, and we call these rocks, these new metamorphic rocks, greenstone and greenschist. Let's have a look at some greenstone. Here's a rock that we've seen so many times, we'll just call it Bobby Joe. This is Catoctin greenstone. This Catoctin greenstone is all over Shenandoah National Park on Skyline Drive. And here's that same Catoctin greenstone in columnar basalt form. Grammy's taking the picture, and this is when we were young whippersnappers, only about 60 years old. Catoctin basalt was erupted when Rodinia supercontinent was rifting apart, and subsequent tectonic pushing and shoving pushed the Catoctin formation up into an anticline, turning it into greenstone in the process. Now let's look at greenschist. How is greenschist different from greenstone? Well, mineralogically, it's not. Let's say you have a mid-ocean ridge situation like our present-day Atlantic mid-ocean ridge with all the basalt that's produced. At some time in the near future, the far future, Africa is going to come back and start shoving this ocean crust toward us. All that water, and when the pressure and temperatures are low, you're going to get greenstone. But then as all this stuff gets shoved up on land when the two continents crash into each other, that's going to apply directed pressure to it, and that's going to green minerals like chlorite especially become smeared out and shiny schisty, and that's why we call it green schist. While I've been talking, we've been looking at pictures of the Ropes Creek metabasalt, which is a green schist, and this represents ocean crust that was shoved up on land. It got caught between the eastern Blue Ridge geologic terrain and the inner Piedmont geologic terrain, and was shoved up on land probably during Devonian Akkadian orogeny. Now let's look at Diabase and Gabbro. Diabase and Gabbro have the same minerals in them as basalt. They're all the same rock, except that Diabase and Gabbro are emplaced as plutons underground, and when those plutons erupt on the surface, we call it basalt lava. Here's some diabase, and diabase is usually emplaced as dikes that are more shallowly deposited than Gabbro. Gabbro is easily deposited fairly deep down. Diabase's great claim to fame is that it is the major rock that does the rifting when a supercontinent rifts apart. It's like the blowtorch that breaks the crust into pieces during rifting. If you look at a geologic map like this piece from Rock D, you can see those red lines that are oriented northwest to southeast. Those represent diabase dikes that did the work of rifting apart supercontinent Pangaea around 250 million years ago during Triassic. Gabbro is a pluton that's emplaced fairly deep down in the crust, where it cools very slowly, and that's why it has big crystals. The slow cooling enables crystal sizes to grow fairly large. And notice the funky shape of these white plagioclase crystals in mafic rocks, especially Gabbro. This is calcium-rich feldspar, and it forms these elongate, pointy kind of crystals, and in this case you've got They're kind of splattered, platy, lath-shaped crystals. Next characteristic of calcium-rich feldspar. Gabbro and Diabase are usually most likely affected by Amphibolite Facies metamorphism. Why? Well, at the deep depths in the crust where Diabase and especially Gabbro are emplaced, there is not nearly as much water as in areas where basalt is emplaced. And also, because of the deep burial, temperature and pressures are usually much higher than those produced in Greenschist facies metamorphism. So you get Amphibolite facies metamorphism. In Amphibolite facies metamorphism, you can get metamorphic banding in these mafic rocks. And also, the main characteristic of these Amphibolite facies metamorphism of mafic rocks is that the pyroxene in these rocks is hydrated, strangely enough, to form a hornblende, which is a kind of amphibole. And that's why they call it Amphibolite. Amphibolite, which is the result of Amphibolite facies metamorphism of mafic rocks like Gabbro and Diabase, is made mostly of hornblende and also feldspar that has both sodium and calcium in it, maybe leaning a little bit more toward calcium rich. We're talking about maybe andesine or maybe labradorite. In these pictures of Amphibolite that we're looking at, the black stuff is hornblende. The white stuff is feldspar. It could be sodium rich, it could be calcium rich, or it could be in between. If I see a lot of patchy or needle shapes in the white stuff, raggedy lath shapes, I'm leaning more toward calcium rich feldspar. If the feldspar, especially if the feldspar is dull in color. If it has a bit of shininess to it, maybe like it does here, then it could have a little bit more sodium in it. Of course, that is the world according to Dan, so take it with a grain of sodium. Here's some Amphibolite from the Carolina terrain. It has some banding. It says Metabasalt on there, and it's pretty fine grain, so it could be basalt that has been affected by Amphibolite facies metamorphism. It could also perhaps be Diabase, Metadiabase. And here's some Lawrenceville, Georgia Amphibolite that shows some metamorphic banding. I think that light colored band, even though it doesn't show very green, is actually epidote. The Lawrenceville Amphibolite is fairly close to and associated with the Brevard Fault Zone. The Brevard Fault Zone is a strike-slip fault where the Inner Piedmont, the Cat Square terrain, and the Carolina terrain slid southwest for about 400 miles during the Devonian Acadian. Okay, most excellent rock buds. That's it for the metamorphism of mafic rocks in pictures. I finally figured out where the camera was on this iPad. Anyhow, thank you so much for watching. Hope you enjoyed this. If so, please subscribe. And this is your Rock Papa saying happy rock hunting. It's perfect weather for what I call drive-by rock hunting. That's where you drive down the road till you see an outcrop or an interesting looking rock. You pull over, you grab it, you throw it in the back of the truck, and you take off. Anyhow, this is your Rock Papa. Papa out.